Hello, I'm Armando Villa, and this is a Pivot Analytics report on Nevada's and the United States COVID-19 cases. So with regards to data collection information, we gathered a lot of the COVID-19 case data through government web pages. That is either through Nevada's DHHS webpage, the Center for Disease Control webpage, but then we also had additional feature statistics that we gathered from either the McCarran International Airport webpage or the TSA.gov webpage. The time frame for Nevada's data was from March 15th through July 16th, while the United States case data was from January 22nd through July 16th. So the variables included within our dataset are as follows. We have the straightforward ones of cases per day, deaths per day, and tests per day. With that said, I wanted to point out that we had the positive percentage statistic, which is just the number of positive cases per day divided by the number of tests performed in a day. For the Nevada dataset, we've included a daily airport arrivals, which are the expected number of individuals arriving in Las Vegas on a given day. And then for the US dataset, we have the TSA throughput ratio, which are the number of individuals that have gone to the TSA checkpoint on the same day as they were last year. So a little bit more on the Nevada case data. The first COVID case did not occur until March 5th, 2020. It has grown exponentially since the start, and there actually seems to be some wandering behavior represented in the realization. This is further pointed out within the sample autocorrelations with dampening autocorrelations, as well as within the Parson window with the max at 0. We will be assuming this is non-stationary, and we will do some transformations to model and fit the data. We've excluded the first 20 observations to not skew our forecast. For the US case data, similar to Nevada's, it has grown exponentially. The one thing about this is that the first case occurred around January 22nd, and it is also wandering is represented within this realization. This is further pointed out with dampening autocorrelations and a max at 0 within the Parson window. So similar to Nevada, we're going to be assuming that this is not stationary, and we're going to actually have to do transformations to properly model and fit the data. One other thing that we'll be doing is removing the first 60 observations since they were also hovering around 0. So for our univariate analysis, within Nevada's case data, we did both a first difference and a first difference plus seasonal equals 9 model. Within that, we gathered 3 different parameters for each of the different model types. And as you can see here, the best model was an ARIMA 1010 model. So we went ahead and forecasted using the ARIMA 1010 model. As you can see within the 7-day forecast, it's a little around 1750, while the 90-day forecast starts to taper off at 2000. So for our next univariate analysis, based on the EDA from part 1, the ARIMA model, we also fitted this model using the first difference plus first difference of seasonal period of 9. As you can see within this table to the right, we did a rolling window ASE score, and it looks as if first that the seasonal 9 model was best. We were a little unsure, so we ended up doing a further analysis with that. And after performing the second analysis, where we had the model essentially fit the last 15 entries between the 2 different data sets, it looked like the ASE score between the first difference model actually outperformed the seasonal model. Because of that, we actually forecasted using the first difference model. And now you can see that within the 2 tables to the right. So part 3, that was just an ensemble model. Essentially, it was just a simple average of the forecast from both models, and that is what you see within the 2 images below. So for the US case data, we also did an ARIMA model for our part 1 of this analysis. We identified 2 different sets of a US first difference, and then a first difference of seasonal equals 7. Doing a rolling window ASC, we identified that an ARIMA 6, 1, 2 with a seasonal equals 7 looked best. And that is what we see here, and we forecasted with a 7-day forecast going all the way to around 80,000 per day, and then the 90-day forecast topping to around 200K cases per day. So for our next analysis, we did another MLP model, and we also use the same as we did within the previous, with the first difference and first difference of seasonal period of 7. And we let the model run, and what we ended up getting was these ASC scores, and it really looked like the median ASC first difference seasonal equals 7 had the best score. So that's what we used moving forward within our forecasts. And this is where you see here that over the next few days, as well as the next 90 days, it continues to increase. So for part 3, similar to the Nevada data, we use a simple average of forecasts from both models. And that is what you see within those images here. So now to our multivariate analysis. So the Nevada case data, we ended up using 2 extra features as explanatory variables to help with a prediction of cases per day. We had tests per day and daily airport arrivals. And with that, we did 3 different models to forecast. We had a VAR model, an MLP model, and an ensemble model. So within the VAR model, it's pretty straightforward when it comes to coding. Essentially, there's this program called var select where it essentially selects the parameters for you by giving it the data, by feeding it the data. With that, it gave us a lag max of 8, and the ASC rolling window scores using a lag max of 8 is shown here. After that, similar to how we did with the univariate, we did an MLP model, except this time we included the 2 extra explanatory variables. The first difference and the first difference plus seasonal equals 9 ASC scores are listed here as well. And then lastly, also similar to our univariate analysis, we got the simple average of both forecasts, and that is what we used for the ensemble model. And as you can see within these 6 images, these are all associated to the forecasts from the previous slide. We have the VAR example, the MLP example, and the ensemble example. The additional details can be found within your report packet, but I just wanted to point out that it kind of ranges from about 1,500 to 2,500 for the 7-day forecast, and then from 12,000 to all the way to 50,000 for the 90-day forecast. Finally, for the US case data, also use the same parameters, except we had different explanatory variables to help with the prediction of cases per day. This time we did tests per day and the TSA throughput ratio. For the VAR model, the VAR select program selected a lag max of 8, and that's how we got these ASC scores. For the MLP model, we did both a first difference and a first difference of seasonal equals 7, and that's how we got these ASC scores. And then the ensemble model is just a simple average of both forecasts. And here are the 6 different images associated to those forecasts. I'm not going to go into too much detail as they're included within our full page report, but as you can see here, the 7-day forecast ranges from around 80,000 to 105,000, while the 90-day forecast is 100,000, up into an exponential growth outside of our chart. So what does all this mean? Well, after running through each analysis, we feel most confident using a univariate approach of an ARIMA model for both the Nevada and US case data. This is further evident by having the lowest ASC scores amongst the groupings. As you can see here at 28.5K for the Nevada data, and then for the 19.9 million for the US data. Now with that said, are there any questions?